I promised you last time that we would start perturbation theory today, and as I realized we still have a little bit left on this proof, and then I looked over other sections in the book, and I realized there's a couple of things that I want to give you before we do perturbation theory. So perturbation theory will start on Tuesday, and then what we're going to do today is we're going to finish up the proof for this amazing result, and then I'm going to just run through some important results from middle chapters. I'll go over that in time, but we won't do proofs. We'll just do things by example. So to get started today, I wrote up the theorem that we're trying to prove, and that theorem is that a matrix A can be diagonalized by a unitary similarity transformation P if and only if A is normal. Okay, so that's a large class of transformations. And the first step in doing that, and if you would like to look at the notes, go back to the next to the last page of notes from last time. But what we did was we took a matrix A and we basically broke it up into two hermitian operators, okay, which are added together with a factor of I in there. This is any A. Absolutely any A can be written this way, okay? So we can take the A and identify the first term as the matrix B, the second term as the matrix C, and what we know is that these are both hermitian. Now, doesn't that mean that A is hermitian? No, because A is the sum of two hermitian matrices, but it's got an I in there. Okay, and that I switches sign when you transpose or when you hermitian conjugate it. So there's no guarantee that A itself is hermitian. That's fine. But what we realize very quickly is if we find a unitary transformation which diagonalizes B and simultaneously diagonalizes C, then A can be diagonalized, obviously, because a diagonal matrix plus a diagonal matrix is a diagonal matrix. Thank you for that rapid answer. At any rate, okay, so the question we have to ask is, can B and C be simultaneously diagonalized? So that really breaks up into two questions. The first question is, because B and C are hermitian, does that mean they can be diagonalized at all? And then the second question is, okay, you'll find out that any hermitian matrix can be diagonalized, but how do you know when these can be simultaneously diagonalized? Okay? Now, we talked about A at the end of the last lecture. And for A, what we found was that any hermitian matrix may be diagonalized by a unitary similarity transformation. So that tells us that B can be diagonalized by a unitary similarity transformation, and so can C. The final part of the proof is addressing question B. That is, when do you know that you can simultaneously diagonalize two hermitian matrices? So I'm going to start with a theorem, and then we'll quickly prove it. So, oh, no, sorry. I'm going to start with a theorem that we'll use in the proof of the answer to this question. So here we go. Two hermitian matrices exhibit a complete orthonormal set of common eigenvectors. That is, these are eigenvectors of both of them. If the two matrices commute. Okay? Now, I'm not going to prove that, That should be obvious. And it shouldn't be obvious in the mathematics sense. It should be obvious in the physics sense. Where have you seen a statement like this? Quantum mechanics. Okay? Think about it. X and P, where this is the x component of the momentum. Okay, these are operators in quantum mechanics that do not commute. And a consequence of that in quantum mechanics is that the basis associated with the x operator is different than the basis associated with the px operator. And this is why if you're a vector along a basis at x, that's necessarily a superposition along p. And if you're a basis vector along p, that's necessarily a superposition of x. Okay? I'm trying to stir your quantum memory. Okay? But what is important is when you have operators in quantum mechanics which do commute. For example, the square of the angular momentum and then the z component of the angular momentum, these operators commute with each other. And what's nice is that the basis in the Hilbert space, I know we're not talking about Hilbert spaces yet, but you looked at Hilbert spaces in quantum mechanics, but the basis of the Hilbert space associated with L squared is the same as the basis associated with LZ. Okay? You can be in an eigenstate of this and be in an eigenstate of this simultaneously. You cannot be in an eigenstate of this and in an eigenstate of this simultaneously. That's impossible. Okay? So hopefully this is digestible from your quantum background. And now all I want to do is take this result, filter it into this story, and show once and for all the validity of this. Okay? Now right now, two hermitian matrices exhibit a complete orthonormal set of common eigenvectors. Well, this is indicating that these two matrices are simultaneously diagonalizable. Okay? So these are simultaneously diagonalizable as long as they commute, but let's see what implication that has for this story. So, recall, here we go, A. So the definition of A in terms of B and C, then what we can say is if B commutes with C, then we can say the following. You know, never in my life, never, ever, did I realize that an exclamation point is an I flipped over. What? I know, it's crazy. I just tried to write an I, but I wrote an exclamation point instead.
We learn new things every day.
I know, it's crazy. There's some kind of parity, reversal, symmetry crap associated with that. Anyway, sorry about that. You should, it'd be awesome. Okay, I'm going to get rid of the factor of 1/2. It doesn't impact anything, and when we have the following. Okay? And Jacob, what is this? It's the commutator of A with A. That's what it is, but what's its value? Zero, yeah. What about this? Also also 0. Good. How is this related to this?
It's the complex conjugate of the.
Well, actually, you don't have to complex conjugate. This is A dagger minus A dagger A. This is A dagger A minus A dagger. How is this related to this? Yeah, it's negative, so that negative cancels, and this just gives me 2A dagger A. Okay? Folks, do you see it? If these two matrices commute, what kind of operator is A?
Hermitian.
A is normal. A is normal.
It's normal.
Yes. Okay, so what we just proved is that you can take any matrix, break it up into the sum of two Hermitian matrices, B and C, and B and C are simultaneously diagonalizable if A is normal. Okay? Are we all on board? Okay, now, a follow-up to that is the following, which is going to make connection with the homework that you just did. You might suspect the following. So we have that normal is diagonalized by unitary, where remember unitary transformations are those that use the Hermitian conjugate or the adjoint of the matrix times the original matrix equals the identity. Okay, so this is utilizing complex matrices. This includes anti-Hermitian as well as anti and normally, so this includes Hermitian, anti-Hermitian, symmetric, anti-symmetric matrices, unitary and orthogonal matrices. Okay? But you might get the idea that if we just take complex numbers out of the story, then maybe what you have is diagonalized by an orthogonal matrix. That's the real equivalent of unitary. Okay? If I take a matrix which satisfies this, but the elements of the matrix are real, then it also satisfies that, which is the orthogonality condition. Okay? So, let's see. If A dagger equals A is realified, then we have A twiddle equals A. We have A dagger A equals I. Realified goes to A twiddle A equals I. And then we have if A dagger A equals 0, that goes to A twiddle A equals 0 as well. Okay? So I'm just saying with the real arrow, if I just restrict myself to real elements and there's no complex elements, or there's no imaginary elements, a real element is a complex element, it just happens to be a complex element with the imaginary part 0. But I get these nice results. It looks like I'm just playing the game, except I'm replacing the dagger with the twiddle. And the twiddle, remember, tells you to transpose only. Okay? Well, here's something suspicious. here's something which makes us pause. Remember, we have the decomposition of A into A dagger plus I 1 over 2I, A minus A dagger. This operator is hermitian. This operator is hermitian as well. Okay? But there is another way we can decompose A. We can decompose A into symmetric. Oh no. That's symmetric, but what is this? It's antisymmetric. These two are both hermitian operators, but if you want to break this up into isometries, into their real analogs, then you actually get a sum of a symmetric and an antisymmetric operator. Okay? So there's certainly a part of the story that won't work out. In fact, you might expect that this part of the story won't work out anyway, because after all, if I take an orthogonal matrix and I use it to transform a linear operator into its diagonal form, okay, what should run down the diagonal? What values? The eigenvalues, right? But let me ask you a question. I start with a real matrix, and I'm trying to diagonalize it using real matrices. Okay, that's what orthogonal means. And the resulting diagonal matrix should have the eigenvalues down the diagonal. Now, who can identify the problem with that story?
Not always real.
Exactly. The eigenvalues of a real matrix are not always real. Sometimes they're complex. And then the question will be, well, where the hell do those complex values come from? I'm taking a real orthogonal matrix. I'm using it on either side of a real matrix. That matrix multiplication is just going to give me real things. Okay? So it turns out that you can't just realify the story. Okay? However, there is one thing you can say, and that is any real symmetric matrix can be diagonalized by an orthogonal similarity transformation. Okay? So it turns out that if you're dealing with a symmetric matrix, that is, the matrix is equal to its transpose, then you can diagonalize it purely with an orthogonal transformation. Okay? However, if you have an antisymmetric matrix, that's where A is equal to minus A transpose, or if you have an orthogonal matrix itself that you want to diagonalize, then you'll find that it cannot be diagonalized by an orthogonal transformation, but it can still be diagonalized by a unitary transformation. You can always diagonalize these by unitary because they're all normal. If you did your homework and you did it as I told you, in problem 3 you demonstrated that. I gave you a symmetric matrix and you diagonalized it with an orthogonal transformation. Then I gave you a matrix which is both antisymmetric and orthogonal, and you found that in order to diagonalize it, you had to use a unitary transformation, not an orthogonal one. Okay? So if you don't get that, go back and look at the answer to question 3 on the homework. Okay. Are there any questions before we move along?
Wait, so can we just, that last thing you just said, so number 3, part B, the eigenvalues do not run down the diagonal?
So what was that matrix? Remind me. I have it up here if you.
It was 0, 1, negative 1, 0.
0, 1, negative 1, 0.
Yes.
0, negative 1, 1, 0. Okay, it's orthogonal, and it's also anti-symmetric, because if I do a transpose, I get minus the original thing. Okay, so that's why I said it's both an orthogonal and an anti-symmetric matrix. Can I ask your question again?
Yeah, maybe I did it wrong, but the eigenvalues did not run down the diagonal. After you find the eigenvalues, and then the vectors, and then you plug them back in to diagonalize it, it didn't work out.
Really? Did anybody else find that?
Maybe I just screwed it over.
Yeah, you might have made a mistake. Yeah, which is fine, which is fine. Yeah, you should have found that the eigenvalues of this included a complex eigenvalue.
Yeah, it did.
Okay, and therefore to get from a real matrix to a complex matrix, you've got to use a complex matrix to diagonalize it. And that complex matrix can't be orthogonal, but it can be unitary. So yeah, so I would bang on that, make sure you get it right. Okay? Other questions before we move on? Okay, so now we're going to have a little fun because I'm not going to do any more proofs. So I'm just going to work by example. And while I'm potentially able to do this in the abstract language of, say, polynomial functions or whatever, I'm just going to use the hell out of matrices. So we're going to get these results represented by matrix examples. Ugh. All right. So this first result, or the first set of results, is going to come from the section in the book called On the Solvability of Linear Equations. So if you want to read that part to reflect on what we're doing today. And let me start with a theorem. If A is a linear operator, on a vector space, V with eigenvalues lambda I, then A dagger has eigenvalues lambda I star. Okay? Now again, there's a proof of this in the book, but I'm just going to proceed by way of an example. An example, of course, doesn't prove anything. An example could be a special case, and then you could do another example later on that contradicts it. But it's fine. We don't have to prove everything. So I want you to consider, for this story, the following matrix. You know what today is?
Thursday.
It's the first day of my chemo cycle.
Oh, no.
I know, which actually means that next Tuesday is when I'm going to shine. Actually, I'll be falling asleep while lecturing next Tuesday. But anyway, yeah, so yeah, I'll make a few mistakes here and there. Those are I's. I. Okay. Now let's bang this out. Yeah, okay, so we've got, all right, so debt. And I did this in gory detail in the notes, but I'm going to write briefer versions of things. We've got I plus 1 minus lambda squared minus 2I lambda minus 2. Okay? So if I want to know what my lambdas are, I can call lambda 1 when this is 0. So that's going to be I plus 1. And then for lambda 2 and lambda 3, I can just demand that this be 0, and then that just uses the quadratic equation to find the lambda. So we'll have 2I plus the square root of minus 4 plus 8 over 2, which is I plus 1. And then similarly, the third is going to be this with a minus, and that's going to be I minus 1. Okay? Notice we have a degenerate eigenvalue, which isn't obvious. I mean, it might be a little obvious, but okay? Now what I want to do is I want to consider a dagger, which is minus I plus 1, 0, 0, 0, 0, minus I, 1, 1, minus I. Okay? And what I'm going to do is I'm going to label the eigenvalues of this just by a lambda star. That's kind of like a lambda prime. It's just a different lambda than the original lambda. It's kind of bad notation, right? Because star means what? Well, what we're going to find is that these lambdas are exactly the complex conjugates of those. So we might as well call them that. But we'll find that they are the complex conjugates. So, oh, sorry. This is 0. All right, so this is going to give me minus I plus lambda minus lambda star times lambda star squared plus 2I lambda star minus 2 equals 0.
Should that be a 1 instead of a lambda?
Sorry.
First lambda you wrote.
Yeah. Sorry, this should be a 1. You're right. I'm telling you, man, that's part of what chemo does to me. It's like, I'll say this and write this, and then I'll write this and say that. Who cares? Anyway, well, hopefully you care. Hopefully you all care. Anyway. So, lambda 1 star, we're going to take this to be 0. Lambda 1 star is minus I plus 1. Notice I'm not taking this and starring it and calling it lambda 1 star. I'm solving this for its roots, okay? Similarly, lambda 2 star, if I plug in, I get minus I plus 1. And for lambda 3 star, I get minus I minus 1. Okay? So as promised by this theorem, if A has eigenvalues lambda I, a dagger has eigenvalues lambda star. Okay? Now, okay. So let us follow with yet another theorem, which says, if lambda I is the spectrum of A, then lambda I star is that of a dagger, then if phi j is an eigenfunction of A that belongs to lambda j, the eigenvalue lambda j, and psi I is an eigenfunction of a dagger belonging to lambda star I, then the inner product of phi j and psi I equals 0, two underlying eigenvalues are different. Okay? God, that's the longest theorem I've written so far. All right. So let's take this example and beat it up a little bit further to demonstrate this. So we're going to need our eigenvectors. So we'll start with the eigenvectors of A. And, well, first of all, we've got this repeated eigenvalue, so we can just find an eigenvector associated with the eigenvalues 1 or 2. And what we find is, and I'll just kind of skip along to be a little bit, well, actually, I'll write this one example up, and then I'll be more brief on the other ones. So we're going to plug in that eigenvector into the original, or sorry, into the matrix minus, no, we're going to just take the damn matrix, and we're going to plug in our eigenvector on the right. So we're going to take the ABC and we're going to multiply it by I plus 1. All right, so what do we have to satisfy? We have to satisfy IA plus A equals IA plus A, IB plus C equals IB plus B, B plus IC equals IC plus C. Is this solvable?
Yeah, if B and C are 0, that'd be cool.
If B and C are 0, this would be cool? Well, if B and C were 0, what are all these terms? They're 0, but does B and C have to be 0?
No.
No, they just need to be
Equal.
equal, right? If B and C are equal, then these last two equations are satisfied. And what value does A have to have? A can be anything you want. So A is anything, and B is equal to C, okay? Anything satisfying those conditions is an eigenvector, all right? Now what we can do is we can take any selection of these as a starting point. So why don't we take A to be 1 and then B and C to be 0. And then we Gram-Schmidt the shit out of it to find a second orthonormal eigenvector. And if you do that, you find a second one. That has that form. Obviously, they're orthogonal to each other, and they're both normalized. Okay? And they both satisfy these conditions. All right? And then last but not least, we have to find the eigenvector associated with the lambda 3 eigenvalue. And now I'm going to be a little bit quicker. I have IA plus A equals IA minus A. IB plus C is IB minus B. And B plus IC is equal to IC minus C. What do these imply about A?
0.
A is 0. What do they imply about B and C?
B equals negative C.
B equals negative C. Okay? So if you want a third normalized eigenvector, there you go. Okay? Notice all these eigenvectors are orthogonal to each other and they're all normalized. So we have a complete orthonormal basis. But what we want to do is we want to show this. So now I'm going to need eigenvectors of A dagger. So again, we have the same eigenvalues, lambda 1 and lambda 2 to start with. And so our story in this case plays out as follows. I'm gonna skip writing this down. You can figure that out. I'm just gonna write what it implies. All right? Therefore, if we want to find the eigenvectors associated with this set of conditions, we can use the same procedure. And then, of course, if we do lambda 3, oh, sorry, this is lambda star. Lambda star is the eigenvalues of the A diagonal matrix. Then this gives me, once again, A equals 0, B equals minus C. Okay, so I have eigenvectors for A, I have eigenvectors for A dagger. Now let's just check this out. Okay? If I take x1 and I do the inner product of it with y2, what do I get? Say it loud, say it proud.
0.
0. Is that satisfying this? Yes, because the lambda that underlies eigenvector 1 and the lambda that underlies eigenvector 2, that's the lambda, not the lambda star, so we star this back. Wait a minute, hold on. Oh yeah, they're different. Sorry, they're different. Yeah. Okay. And the same goes for if I do any of the, no, hold on. Hold on a second.
According to that, shouldn't the inner product of x3 and y1 be not 0?
Is it more important that?
Yeah, hold on a second, hold on a second.
Well, I guess they don't.
Is
Negative
it that I doesn't get?
I guess this makes sense.
Hang on a second.
So like what we have matches that here.
Yes, the only way to get a non-zero inner product is to take, in this case, the inner product of a vector with the corresponding eigenvector in the A dagger case. Yeah, but that's of course having the same eigenvalues. Yes?
But one thing, like we could swap y1 and y2, then this wouldn't hold.
Well, where does y1 come from?
Lambda 1 or lambda 2, because they're the same. Like those are bounded by the same conditions, so.
Yeah, that's actually a good point.
It's not whole.
We broke math.
Yeah, no, hold on, I'm gonna have to think about this for a moment.
Pure physics on board.
That's terrible, it's horrible. Be really careful. Yeah, be really careful about reading this. What is this saying? It's saying that these are 0 if lambda I is not equal to lambda j.
It's only one F?
It's not, well, no, it's only one if. It's not saying that if lambda I equals lambda j, then this is non-zero.
Right.
It's not saying that.
So only for the ones where the original eigenvalues don't match.
Yes,
So we
then,
just have x1 and y3.
yes, so, right, and I like what you said about it's not the if, it's just the if, okay? So this is saying this is gonna be zero if these are different. But it doesn't mean that if these are the same, then this is not zero. And that's what we just discovered on this awesome example that I put together.
So
This is not in the book, so, but anyway, go ahead.
does this hold if A's eigenvectors are not orthogonal? Because here A's eigenvectors were orthogonal, and then A dagger just had the same eigenvectors, so it was nice and easy that way.
Yeah, if you actually just hold the conditions in each one, then you'll find that it holds based on the conditions instead of picking this particular starting point and then getting an orthonormal vector. You don't have to do that.
But I mean because not every matrix has orthogonal eigenvectors,
Okay.
right? So, like in this case, A had orthogonal eigenvectors, and then A dagger just had the same eigenvectors, so it worked. If A's eigenvectors were not orthogonal, then would A daggers be different such that it still holds?
Yes. Yeah, unfortunately, I picked an example which is, like I said, you can't prove anything by an example.
Could you say, like, is it a thing that if a matrix has orthogonal eigenvectors, then the hermitian conjugate has the same eigenvectors?
Yes.
And you could show that with this theorem.
Yeah. Okay. Other questions? Comments? Okay. There is yet another theorem which says consider A, and I'm just trying to get all of the theorems and definitions that are in the book on the board. Some of them are not really that interesting. If I consider A with lambda and A dagger with lambda star, that's the matrix and the eigenvalues, the matrix and the eigenvalues. The geometric multiplicity of lambda is the same. As lambda star. Okay? And that obviously is reflected in this example. Okay? We have one eigenvalue here, but its geometric multiplicity is 2. You have 2 eigenvectors. Okay? And you have 2 eigenvectors associated with that same eigenvalue in this case. It's an example, it's by no means the proof. You want the proof? Look at the book. Okay, now I'm going to finish. Well, I'm not going to finish. I still got a bit more to go, but oh goodness. But now we're going to write up another thing up here, which is a bit more powerful. So how many of you remember when I wrote up the theorem, if the determinant of a matrix is 0 and the eigenvectors span the space, then the equation AX equals B has a solution only if B is a linear combination of eigenvectors for which the eigenvalue is not 0. Does anybody remember that? Okay, look back in the notes, and I do that, and I do an example. Okay? We're going to write down a similar theorem based on this context. The equation A minus lambda I x equals y has a solution if and only if phi I x equals 0 for all phi I satisfying a dagger minus lambda star I phi I equals 0. Okay? Notice these are different equations. So let me get rid of all this. And I'll regret it later on, but so consider the following. We're going to work with the same A that we've been working with. That way we can reuse all of its stuff. So for A, let's take the first eigenvalue, and then we'll form the following. I plus 1 minus I minus 1, 0, 0, 0, I minus 1, 0, or sorry, 1, 0, 1, I minus 1. Okay, this is A minus lambda I. That right there. Times A, B, C. This is our X. And then this will simplify to the following: 0 minus B plus C, B minus C. Okay? So we're going to look for a solution to this expression. Now, what we want to do is we want to write this out and then use this condition to verify. So let me very quickly write this down. So now we're going to have minus I plus 1 plus I minus 1. Oh. Zero, 0, 0, minus I plus I minus 1, 1, 0, 1, minus I plus I minus 1 on A, B, C. This is A dagger minus lambda star I. Okay, so I'm just taking the hermitian conjugate of A and I'm subtracting off the complex conjugate of this times the identity matrix. That's where this comes from, okay? These are the elements of phi. That's this guy right here. And I want this to be equal to 0. Okay? And this ends up giving me that phi equals A, B, B. Okay, so A can be anything, and then the B and the C elements just have to be the same. If that's the case, then this is satisfied. The work is done in the paper, in the notes, but I just got to be abbreviated here. Now we can again take phi 1 to be 1, 0, 0, and then Graham-Schmidt it to get a phi 2. Okay, and now what I want to do is I want to let y here be equal to 1, 0, 0. Okay? Now if y is equal to 1, 0, 0, What is the inner product of y with phi? Is it 0?
With phi 1.
Well, with phi 1, no. Okay? Huh. Well, that means that if I take the y here to be 1, 0, 0, then by this theorem, there should not be a solution to this. Let's see. Okay? Well, I got 0 equals 1, minus b plus c equals 0, b minus c equals 0. Can you tell me the values of b and c which make all of these true?
B equals C. 0 equals 1.
Yeah, 0. This is the fucker. Yeah, there's no solution. Okay, let's try one more and then we'll do a successful one. If I take y equals 0, 1, 0, the inner product of y with phi 2 is 0 or non-zero? Non-zero, so we don't expect a solution in this case either. And in this case, we get 0 equals 0, that works out. But then we get minus b plus c equals 1, and b minus c equals 0. That's literally just taking this and putting it right there in this. Okay, you see that? Is there a solution to that? No. Go ahead and ask your question.
So we're saying the inner product of y with b is non-zero,
Yes.
but in the theorem it says x with b.
Oh, shoot. Oh, sorry. This should be y. My bad. Sorry. Miswritten. Thank you for that correction. I'm going to come back to you guys for another correction in a minute. Okay, let's try one that actually works. Y is 0, 1, minus 1. Right? Inner product of that with phi 1 is 0. Inner product of that with phi 2. It's also 0. Okay? So what does this give us? This gives us 0 equals 0, minus b plus c equals 1, b minus c equals minus 1. Holy shit. Look at that. Okay? So obviously a being anything, b being anything, and then c being minus 1 plus b is a solution. Okay? All right. God almighty, I cannot proceed that quickly. All right, I'm going to try and bust through this really quickly because I really want to start on perturbation theory next week. So are there any questions about this before we press on? Okay. Now that all came from the chapter on the solvability of linear equations. Now I'm going to skip to the chapter of minimum principles. Oh man. And I will basically just focus on the first theorem that came from this section. Bye-bye. And then in my notes, my lecture notes, I'll have written up the other theorems, the definition, and then I'll talk a little bit about the an example for one of the later theorems. But this is the theorem I really want to talk about. And this is rather interesting. If A is self-adjoint, AX equals lambda x if I, which is x, AX, the inner product of x with AX, is extremized with respect to the constraint that the inner product of x with itself is 1. And in fact, the value of I, when extremized, will be lambda. So this is a relationship between extremizing this function and finding eigenvalues and eigenvectors. So I'm going to do this rather quickly, so bear with me. I want you to consider this matrix A, and I'm doing this hella large because it will feed nicely into another example, which I won't get to, but all I've got is the hella large example down. It's funny, I had a 3x3 example, and then I was like, oh, I can't cover this other theorem as part of this, so I've got to go to 4x4, and now I'm not even going to do it. Anyway, okay, so first of all, A is a dagger, so A is normal, okay? And the eigenvalues of A are and this is just in no particular order, 3, 5, 1, and 1. And I'll just refer to those as lambda 1, lambda 2, lambda 3, lambda 4. And then the eigenvectors are x1 is A, 0, 0, 0. x2 is 0, B, B, 0. x3 is 0, A, B, C, with A plus B plus C equals 0. And x4 is 0, D, E, F, with D plus E plus F equals 0. Okay, we can obviously normalize these. Okay, can't really normalize these until we make some picks. But at any rate, so now what I want to do is I want to fashion this quantity I. So we're going to take I as A, B, C, D. That's just the components of X. And we're going to make everything's real in this case, so don't worry about complex conjugating things. And then we'll just do A. I'm not going to write A up there again. Okay? So this is this object I. And then if we bang it out, it's going to give us this. Okay? Subject to, of course, x, which is a squared plus b squared plus c squared plus d squared equals 1. And then what we want to do is if we have something we want to extremize, but we're going to subject it to this constraint, then we should effectively use something called a Lagrange multiplier. Okay? So what we can do is we can form J, which is I minus, and I is this, not the identity. J is I, well actually, sorry. Okay, so let me say that K is I minus lambda J, where J is the constraint equation where it equals 0. So this is obviously a squared plus b squared plus c squared plus d squared minus 1. Okay, that equals 0. So we form this K by taking I and subtracting a Lagrange multiplier, lambda, times J, and that's going to give us 3 minus lambda a squared, is after some rearranging. Okay? This is all trivial. You know, given this, which you should be able to get just by putting the A matrix in here and multiplying it out, and then taking the J, forming I minus lambda J gives you this expression. Okay? And now, to extremize this, but holding this true, what we want to do is just demand that dKA equals 0. But dKA is 6 minus 2 lambda times A, so we want that to be 0. We want dK dB equals 0. This is 1 minus lambda 2B plus 4C plus 4D. We want that to be 0. We want dK dC equals 0. This is 1 minus lambda 2C plus 4B plus 4D. And we want dK dV equals 0. Okay? All right. Now, now what I'm going to do is I'm just going to turn the dial on lambda. I'm going to adjust the value of lambda and see when there exist solutions. So if lambda is equal to 3, hold on a second. Yeah. If, sorry, there's something in my notes that I have to follow. But anyway, you'll figure it out with it in a second. If lambda is equal to 3, then what do I find? Obviously, A is equal to 0. Oh, sorry, no, this is 0. So 0 times A is 0, lets A be anything. And then we have minus 4B plus 4C plus 4D equals 0, minus 4C plus 4B plus 4D equals 0, and minus 4D plus 4B plus 4C equals 0. Okay? Just plug a lambda equals 3 into each of these, and these are the resulting equations. And this, of course, implies that A is anything, while these imply that B is equal to C is equal to D is equal to 0. Okay? Notice, I'm not finding an eigen, I'm just extremizing this function subject to this constraint. But when lambda is equal to 3, I'm generating the exact same eigenvector. Which if you normalize it, you just get 1, 0, 0, 0. Okay? If we do lambda equals 5, then very quickly we have minus 4a equals 0, minus 8b plus 4c plus 4d equals 0, minus 8c plus 4b plus 4d equals 0, minus 8d plus 4b plus 4c equals 0. What does this tell us about A?
0.
What does this tell us about B, C, and D?
They all need to be equal.
If they're all equal. Okay?
That's not an eigenvector.
No, hold on. Shh.
We can just end here today, it's okay?
No, hold on. sorry. I did not mean to do this. I'm sorry.
For anyone who writes it
Yeah, I
down.
wrote this down wrong. Okay, yeah, sorry about that. Yeah, obviously, look, folks, I wish you had told me this was not orthogonal to this. It is now. Everybody see that? I mean, I just made a mistake. It's right in my notes, but I just wrote it down wrong. I do that occasionally. Okay? And now clearly this matches. Okay? And by the way, if you evaluate the value of I using this solution where it's normalized, you get I is equal to 3. If you evaluate I in this case, you get I is equal to 5. Okay? Now, very quickly, I'm going to do the last one for a very specific reason. All right? So if lambda is equal to 1, then this is the conditions that have to be met. 4a equals 0, 4c plus 4d equals 0, 4b plus 4d equals 0, 4b plus 4c equals 0. What does this tell you about a? What do these tell you about B, C, and D?
You need to add to 1. Or they add to 0.
They have to be 0. Huh. Well, they do add to 0, but it's not very interesting. Huh. What in the world could be wrong? So this is me tearing my hair out when I'm preparing this lecture, because I'm like, shit, it doesn't work. It doesn't work at all. No one can pick it out, it's fine.
Well, I mean, it works if you just set A, B, and C to all be 0 in X3. That's allowed.
That's not a normalized X.
Yeah, okay, now, in all honesty, I'm gonna go back. This is wrong. What I showed you last time was actually wrong. And you could have seen it from two different perspectives. One, you could have seen it from just finding the eigenvalues of this, because it turns out these are negative. But then you also could have found that plugging in +1 as an eigenvalue does not give you this as a solution. Yeah, I made a mistake. I put +1 instead of -1, but that is exactly what cures this. Because if you put in +1 and -1, then this gives you 4a, sorry, 4b, 4c, 4d.
Oh my god.
And now what do you have to have A, B, and C, A, B, C, D follow in order to be a solution?
Add to 0.
Okay? So it works out. When you read my notes, you should notice the notation, because I've got all those corrections in parentheses, because I don't want to mention them to you until you realize the mistake we made last time. All right, remember there'll be an extra page of notes going over some extra stuff associated with this. It's not that significant, but we're going to get started on perturbation theory on Tuesday. Thank you very much.
This is all just practice for after you get your chemo callbacks, and you're making mistakes, we realize them.
Yeah. Okay, they're gone.